UJT is a unijunction transistor. UJT is a unijunction transistor and it belongs. It
Screen is not.
belongs. Screen नहीं आ रही है? Okay, I'll share it again. So unijunction transistor, it basically belongs to Thyristor family. Thyristor family. Okay. Thyristor, it is actually a 3-junction 4-layer device. Thyristor, as you know, BJT, BJT is a 2-junction 3-layer device. You have emitter, you have base, then you have collector. So you have 2 junctions, okay? So it is a BJT, it is 2-junction, but 3-layer device, 2 junctions. So you have 2 junctions here. But Thyristor, it is a 3-junction 4-layer device. Thyristor is a 3-junction and 4-layer device. Okay, 3-junction, 4-layer device. There will be a separate course in your engineering on thyristors, which is known as power electronics. Probably in 7th or 8th semester, you will be studying thyristors in detail. Thyristors are special semiconductor devices which are generally used for triggering circuits. Okay, so whenever you want to trigger a circuit, trigger means turn it on at certain instant. Then you have a triggering mechanism which is being realized using thyristors. So you have a variety of circuits using thyristors. You can make rectifiers, you can make motor drives, you can make semi-converter drives. So there are even you can make cycloconverters. There are a lot of circuits that you will be studying in your course. So I will not spend time on thyristors. That is beyond our scope right now. But what I want to say is that UJT belongs to Thyristor family. What is a Thyristor family? What is most peculiar to Thyristor family? That they are used for triggering operations. Okay, I'll also explain some of the things. And we should remember that the UJT, this UJT has a high impedance. It has a high impedance in off state. Okay, off state. How is UJT realized? What is its structure? I will also draw the diagram, but I'll write down few sentences that will help you in understanding that diagram very efficiently. So UJT generally has very high impedance in off state, and it has a low impedance in on state. So that is one of the important feature uh, of the UJT. When it is on, the impedance is very low. That means charge can flow very easily. When it is off, the impedance is very high. It has high impedance. Okay. And because of this, this is similar what happens in thyristor also. In thyristor, you also have a very low impedance during on operation and you have a high impedance during off state. Okay. So this is similar to thyristor. Similar to thyristor. Thyristor. This is similar to thyristor. Okay. And therefore, moving from on state to off state, which is known as switching. Switching is the operation, which means uh, moving from on state to off state. So switching from the off state to the on state in UJTs or even in thyristors, however, is caused by conductivity modulation. So we have to remember that once we change the state from on state to off state or off state to on state, which is known as switching operation. Okay, switching is nothing but changing the state of a device from on to off or off to on. So switching activity here from off to on to off is caused by the conductivity modulation. That means in off state, you have already certain conductivity. Okay, then you modulate it, you make a different conductivity, then it becomes an on state for the device. So how do we differentiate on state and off state in these devices? By actually conductivities. We modulate the conductivity by certain mechanism, and that is how we say device is on and off. ठीक है, मैं इसको अच्छे से explain करूंगा. I'll try to explain it in a better way once I'll draw the diagram. So switching is however caused by the conductivity modulation and not by regenerative regenerative not by regenerative bipolar transistor action. So whatever we have seen in the transistor bipolar BJTs, the same kind of operation is not being it is not true here. And the way BJT used to be turned off or on, same thing is not happening here. We have a different kind of mechanism here, okay, that is helping us, or that makes us understand how the device turns on and off. Okay, I'll just write few points, and then I'll draw a diagram. These points will be more clear. Now, like BJT, the UJT is also a three-terminal device. It is also a three-terminal device. Okay, like BJT, UJT is also a three-terminal device having one emitter junction. So it has one emitter junction and it has two base junctions. Two base ohmic contacts. So जो UJT है, it is also a three-terminal device, but normally in BJT we have emitter, base, and collector. Here you have emitter and you have two ohmic base contacts. Okay, you have two ohmic base contacts. I'll draw a diagram that will be more helpful in understanding this thing. Let me draw it here. This is a schematic diagram of UJT. Okay, so this is how the UJT will look like, or how it looks like. So we have something like this. This is P-type semiconductor. This is a P-type semiconductor, okay? And a connection with this P-type semiconductor, this is known as emitter. So you have emitter here, okay? The current that will go through the emitter, it is IE. Okay, this is IE. And at the top, you have one contact here, which is base B2. At the bottom, you have another contact here. This is base B1. Okay, so I'll write it down, base 1, which is B1. So this is base 2, base B2. Okay. And this entire black bar, which is a bar type structure, it is nothing but it is N-type semiconductor. N-type semiconductor. Okay, this entire black is N-type semiconductor. Then this base B2, it is connected with a voltage source, which is known as VBB, which is a voltage, variable voltage connected between two bases, base B1 and base B2. This is the construction, okay? And this is an ohmic contact. It is ohmic contact here of base B2. Similarly, we also have ohmic contact of base B1 here, okay? Ohmic contact of base B1 here. For emitter, you also have a voltage supply here, which is known as emitter voltage. So you have emitter voltage as VE, okay? VE. So this is emitter voltage, and we have ohmic contact with the base, okay? Now see, you have a p-type semiconductor here, somewhere here. This is p-type semiconductor, okay? I'll draw it with the help of, say, for example, yellow. So you have a p-type semiconductor, and you have n-type bar, p-type dot and n-type bar, okay? So it can form a p-n junction also. It can form a p-n junction. And this entire thing, this entire n-type bar that is all over here, we know that if we have a semiconductor bar, it acts as a resistor. It acts as a resistor. So we can assume that this entire bar, it is made up of uh, two different resistors. Okay, let us assume, because semiconductor bar is nothing but it is a resistor. So once we have a semiconductor bar, its equivalent circuit, electrical equivalent circuit, is nothing but a resistor. Okay, so we have a semiconductor bar here. We are assuming that this bar is nothing but it is our semiconductor resistor. Okay, it's a resistor. So for this diagram, please remember that the UJT has it is a three-terminal device having one emitter and two base ohmic contacts. Okay, two base ohmic contacts. One is base B1, another is base B2. Okay, now the device is this device. Okay, I'll show you the diagram again. The device has evolved from the alloyed germanium bar structure. So the n-type semiconductor mostly is made up of germanium. Okay, it is mostly made up of germanium. Now see, if we draw the equivalent circuit diagram of this schematic representation of UJT, this is nothing but schematic diagram of UJT. Schematic diagram of UJT. This is not the symbol yet. Okay, ये symbol नहीं है, symbolic diagram इसकी नहीं है. अगर हम इसका equivalent circuit draw करेंगे, its equivalent circuit would look like something this. Okay, let me draw it like this. Just give me a second. Okay. So if we'll draw the equivalent circuit diagram of this structure, it will look like this. See, from base B1 and B2, you actually have two different resistors. Okay, so two different resistors means you have a resistor bar. We have a resistor bar. Okay. So this is B2 point and this is B1 point. Okay, this is B2 and B1 point. Uh, why I have made it two resistors here, I'll tell you later on. So let us say that this N-type semiconductor, it is made up of two different resistors. One is RB1, another is RB2. Okay, RB2. Now the conductivity actually will be different from this point to this point in the bar and from this point to this point. You actually have different conductivities. Why? You have different lengths and there is an emitter junction near the B1 and it is quite far away from B2. That is why there will be conductivity is different. I'll tell you how the conductivity will be different. That will be later on. Okay. Now see the conductivity in this portion, it will be G1. Okay. G1 will be equal to 1 by resistance. This is the conductance. Okay, conductance will be G1 will be equal to 1 by RB1. Similarly, G2 here will be equal to 1 divided by RB2. 1 divided by RB2. Okay, 1 divided by RB2. Now you know at this point there is an emitter. Okay, there is an emitter here. From the schematic diagram, we have emitter here. And emitter forms a PN junction at this point. Emitter forms a PN junction. Okay, because you have P-type semiconductor that is being fused to N-type semiconductor. N-type semiconductor. To N-type semiconductor. So we'll draw a PN junction here. So we will have a PN junction. You have N-type here and you have a P-type here. Okay. What is this? This is emitter junction. So whatever voltage is applied here, it is VE. Voltage applied here is VE. Okay. And whatever current will flow inside the PN junction, it is IE. This is IE. Whatever voltage is applied at B2, that is nothing but it is VBB. Okay. VBB. VBB. So this is the equivalent circuit of this entire schematic. Now I will mark two more components here. Okay, two more resistances in parallel with this. One is known as GP, another is G of N. GP and GN, these are excess hole and electron conductances between emitter and base 1. Okay, so I'll write down them. I'll explain them later on. GP, comma, and GN are the excess hole and electron conductances between the emitter and base B1 and base B1. Okay, that is what GP and GN are. GP and GN are. Okay. रोल नंबर 67 बेटा आपको ये समझ में आ रहा है वट एवर आई हैव ड्रॉन रोल नंबर 67 शहाब है हाँ कोई सवाल तो नहीं है
तो ये B2 और B1 बेस क्यों दो होते हैं इसमें
ये असल में दो टर्मिनल्स हैं हमने इनको रखा है नाम बेसिस B1 एंड B2 वो इसलिए हमने बेस इनको रखा है नाम क्योंकि इसमें कंसंट्रेशन ग्रेडियंट नहीं है जो एन टाइप सेमीकंडक्टर है व्हाटएवर दिस यू हैव एन टाइप सेमीकंडक्टर बार जो इसकी कंसंट्रेशन यहाँ से है वही कंसंट्रेशन यहाँ है, और द कंसंट्रेशन ऑल अलोंग द बार इट इज यूनिफॉर्म। क्योंकि कंसंट्रेशन डिफरेंट नहीं है तो हम इनको डिफरेंट नाम भी नहीं दे सकते हैं। अब हम इसको रख सकते थे नाम कलेक्टर एंड बेस, लेकिन तब उसके लिए एक शर्त है, द कंडीशन इज दैट you should have different concentration, doping concentration. Since the doping concentration along the bar it is uniform, we cannot name them differently. So we have just named them base B1 and B2. Now, why we have differentiated with B1 and B2? Because one base is near the emitter junction, another base, another contact. What is base? Base is nothing but the contact. It is the contact point. One contact point is near the emitter junction, another contact point is away from the emitter junction. ठीक है? और कोई सवाल तो नहीं है किसी को? शहाब इज हियर। शहाब,
यस सर।
हाँ बेटा, आपको ये समझ में आया?
जी
फातिक को
सर,
समझ में आया?
सर।
फातिक को
जी
आया?
सर, जी सर, जी जी सर, जी
कोई क्वेश्चन तो नहीं है?
जी नहीं सर जी।
ओके, ठीक है, ऑलराइट। तो इसको, इस डायग्राम को आप अपने जहन में रखें, मैं और कुछ पॉइंट्स दिखाऊंगा एंड फिर हम आगे इसका ऑपरेशन भी एक्सप्लेन करेंगे, ठीक है? So equivalent circuit, this is equivalent circuit of UJT. I'll write down here. This is equivalent circuit diagram of UJT. Equivalent circuit diagram of UJT. Okay. Now see, in normal condition, the base B1 terminal is grounded. It is grounded. Okay, normally जो base B1 है, that is the lower terminal. Base B1 means lower terminal. It is generally grounded, so you can mark this as a ground. Okay, you can mark it as a ground. B1 को हम ground कर सकते हैं. So normal operation में base B1 is grounded and a positive bias is and a positive bias of VBB is applied to base B2. Okay, base 2. Base B2 जो है उसमें हम positive bias apply करते हैं normally, और base B1 is grounded. Base B1 is grounded. Okay. Now see, the resistance between base B1 and B2, the resistance between base 1 and base 2, that is B1 and B2, and or I will say base B1 and B2 is designated, it is designated by RBB. Okay, RBB. Now see, what I want to say is that the resistance between base and B1, base B1 and B2, okay, the resistance between base B1 and B2 is designated as RBB. Okay. So what is RBB equal to? RBB, if we'll see from the diagram, let us see from the diagram, RBB is equal to RB1 plus RB2. Okay, because you know that these two are in series. Okay, this and this, these two resistances, they are in series. The equivalent resistance will be their sum. So you have RBB from base 1 and base 2 resistance, and it is equal to two different resistances, RB1 and RB2 in series. So I say that is designated by RBB, which is equal to RB1 plus RB2. Okay, RB1 and RB2. So here also, this is RB1 and RB2, RB1 and RB2. RB2. Okay. So what is RB1 and RB2? RB1 is actually resistance between base B1 and point A, anode point A. Okay. And RB2 is resistance between B2 and A. So now we have another point here. So I'll mark this point A. You have, for example, point here A. Okay. So whatever is between A and B1, that is known as RB1. Whatever is between resistance between A and B2, it is known as RB2. Okay. Similarly, GP and GN are excess hole concentrations, excess hole and electron conductances between the emitter and base 1. Okay, that I have already mentioned here, between emitter and base 1. Anyway, now VBB, which is connected at the top, VBB that is connected at the top here, VBB, what is the job of VBB? Okay, this voltage actually establishes the current inside the n-type bar. This voltage actually establishes the current between RB1 and RB2, or it establishes the current inside n-type semiconductor bar. It establishes the current inside n-type semiconductor bar. So I'll write down here VBB, okay, establishes a current and an electric field along the semiconductor bar. What is semiconductor bar? N-type semiconductor bar. Okay, and produces a voltage on the n side of the emitter, n side of the emitter junction. I'll explain this line, okay? Which is fraction neta of applied voltage VBB. Now see, what is the job of VBB? Here, VBB actually, it establishes current in the semiconductor bar. What is semiconductor bar? It is n-type semiconductor. ठीक है, इसमें जो current जाएगी, flow हो जाएगी, ये उसको establish करता है, VBB. That is its job. The second thing it does is it also creates a voltage at point A. ठीक है? Because in PN junction that you have here, there is a voltage applied on the P side. P side से एक voltage apply हो रही है. Okay? You have a voltage which is applied on P side. So that is somewhere here. Okay? At here. But N side से कौन सी voltage apply हो रही है? N side से you do not have voltage. Okay? So VBB, once VBB is applied here, it creates a voltage here. It creates a voltage at point A. So what is that voltage equal to? It is fraction of VBB. Because if you see that RB1 and RB2, they act as a voltage divider network. Okay, in this circuit, they act as a voltage divider network. So they act as a voltage divider network. If you have a voltage divider network, then voltage at point A, which is equal to VA, it is fraction of VBB. ये एक छोटा सा हिस्सा है VBB का. Okay, it's not exactly equal to VBB, but it will be less than VBB. You know that in a voltage divider network, if you have a voltage divider network like this, and you have V input is the voltage, then for example, this is the V1, then you can calculate V1, it is equal to, if this is R2, this is R1, then it is equal to R1 into V input divided by R1 plus R2. Okay? So it is a fraction of V input, fraction of the voltage applied. Similarly, whatever I am saying that the voltage applied at point A, it is fraction of VBB. It is fraction of VBB. So what is the job of VBB? VBB establishes the current A and an electric field along the semiconductor bar and produces a voltage on N side. What is the N side? N side is this point. Okay. N side is this point. N side is here. So it creates a voltage on N side of the emitter junction, which is fraction given by neta, fraction neta of voltage VBB, यानी वो इसका एक fraction है. And how much is that equal to? अगर हम देखेंगे वो कितना है, fraction neta will be equal to, यही equation जो मैंने यहाँ पे use की है, this equation, I will use same equation there also. Okay, so I will use same equation there also. Neta will be equal to, what is neta? Neta is VA divided by VBB. Okay, neta is, because what is VA here in this voltage divider network? VA, if we will say VA is equal to RB1 divided by RB1 plus RB2 into VBB. Okay, so if we will take VBB on this side, on left hand side, तो ये divide हो जाएगा. It will be VA by VBB. Okay, so what is neta? Neta is the fraction VA divided by VBB, which will be equal to RB1 divided by RB1 plus RB2. Okay, so what is RB1 plus RB2? RB1 plus RB2, it is equal to RBB. So we can write down it is RB1 divided by RBB. Okay, RBB. RB1 divided by RBB. Okay. Now see, this is the fraction of voltage, or this is the fraction neta that is applied on the N side of the emitter. Okay. Now see, we will take cases here. We'll take cases here. When when emitter voltage VE in this circuit, when emitter voltage VE is less than, what is now VA? VA is less than VA. VA is nothing but it is RB1, or I will say like this. This is neta times VBB. Okay, neta times VBB, because this entire thing we saw that it is equal to neta. Okay, this is equal to neta. So when VE is less than neta times VBB, when VE is less than VA, okay, then the emitter junction, it will be, then what is emitter junction then? I'll ask students, they will help me in identifying the state. Roll number 47, please turn on your mic. Roll number 47.
Yes, sir.
जी हाँ बताओ बेटा, जब VE will be less than, VE is this point, okay, VE is somewhere here, if you can see it, VE is somewhere here. If VE will be less than VA, so VA is somewhere here, you have VA here. So if VE is less than VA, what will be the junction? PN junction forward bias होगा कि reverse bias होगा? What about Zishan Shah, roll number 52?
Sir, forward होगा.
Forward bias? Okay.
Yes, sir.
Okay, turn off your mic. What about Zishan Shah? Zishan?
Forward bias, sir.
Forward bias? तो इसमें दो words हुए. What about Misbah Manzoor? Misbah Manzoor.
Sir, reverse bias.
Very good. It will be reverse bias. It will be reverse bias. It will not be forward biased. Emitter junction is reverse biased. Why? Why will be emitter junction reverse biased? It will be, diode will be like this. VE is less than VA. VE less than VA means you have more positive here. More positive here. You have less positive here. Okay? When you have less positive on P side and more positive on N side, then it will be reverse biased. It will be reverse biased. Okay? It will be reverse biased. So that is why it is reverse biased. So emitter junction is reverse biased. And if it is reverse biased, emitter junction is reverse biased, and only a small reverse saturation current flows through it in emitter circuit. If junction is reverse biased, if diode is reverse biased, what will be IE? IE will be equal to very small amount of reverse saturation current of the diode. It will be very small saturation current of the diode. That means emitter circuit में current flow नहीं होगी. इसमें जो current flow होगी, it will be very small, equal to reverse saturation current. Reverse saturation current. We have already discussed reverse saturation current in PN junction in detail. I don't think we need to explain it here also. But what happens if if the voltage VE exceeds neta times VBB? If VE exceeds neta times VBB, yani VE is more than neta times VBB, I'll ask students to help me to determine the state. Umar Bashir, roll number 76.
Yes, sir.
If VE exceeds neta times VBB, okay, or VA, if VE exceeds VA, what is the state of the diode?
Sir, forward bias.
Are you sure it is forward bias?
Yes, sir. So P side होगा ना sir, फिर positive.
हाँ, diode is forward bias. Very good. Then the junction is forward biased. Okay, diode, or I'll say junction. Junction is forward biased. तब जो होगा diode होगा forward bias. ये सही बात है. So if voltage VE exceeds neta times VBB, by an amount, in fact, कितना होना चाहिए exceed? By an amount to forward voltage drop, या built-in voltage जो होता है diode का, अगर वो उससे ज़्यादा exceed हो गई, because यहाँ जब PN junction, when you will have a PN junction, then you will have VBI also, built-in potential. You will have a built-in potential also here in the diode. So when VE will exceed VA by an amount greater than VBI, okay, then it will be forward bias.
Excuse me, sir.
हाँ जी बताइए.
सर जब VA जब कम होगा ना सर, इससे सर जब रिवर्स बायस होगा,
हाँ,
तो सर I स्मॉल होगा, तो क्या हम वो नेग्लेक्ट कर सकते हैं?
वो हम बाद में देखेंगे यहाँ नेग्लेक्ट होगा कि नहीं होगा. आई विल ड्रॉ VI कैरेक्टरिस्टिक्स, उसमें उसको दिखाएंगे हम. वो नेग्लेक्ट तो हो ही जाएगी, उसका इफेक्ट क्या होगा? That is actually the question. What will be the effect of IE? Okay, if it is in forward bias, and it is a forward current, or when it is a reverse saturation current. So in both the cases, what will be effect? That I'll explain. अभी ये discussion थोड़ा incomplete है, but surely I'll tell you whether we can neglect it or not. Okay. The question is not actually here, should we neglect it, but what should be its effect? इससे क्या असर पड़ेगा circuit पे? That is the question. If you have any question, you can ask me. Otherwise, I'll stop here and I'll continue this lecture in the discussion in next lecture. अगर किसी बच्चे को कोई सवाल